Okay, so let's begin by reviewing. We've now covered this material about classical mechanics, so we've taken a break from our general relativity. So back in lesson 22, we introduced the geodesic equation for the Schwarzschild metric. So here's the general geodesic equation. In lesson 22, we calculated each of these connection coefficients for the Schwarzschild metric. We assume the Schwarzschild metric as a given. We just assume that G mu nu equaled this object here, which in this case I've already chosen C equal to 1. Later on in our development, just for clarity, I put in the C squared here for to capture the fact that our units we're set C squared to 1, but that we're trying to measure everything in terms of meters. There's some development that I follow that keeps that C squared in there, so I returned it later on in our work. But regardless of whether the C squared is there or not, when you see it, you can always replace it with 1. And we remembered that this was the Schwarzschild radius. I keep saying that. This is the Schwarzschild radial coordinate. The Schwarzschild radius is alpha, which is equal to 2m. I've frequently called this guy in past lectures the Schwarzschild radius, but I mean the Schwarzschild radial coordinate. Alpha is actually the Schwarzschild radius, and it's the only characteristic length in the problem. So we knew we were given this as an assumption. Now, later on in our work, we will derive this from the Einstein equation. But part of the development that I promised is given a metric of spacetime, or actually given a spacetime. Remember, given the metric is the same as having a spacetime, right? That's the same thing. And remember, this is, of course, a function of spacetime. Given this metric, so we took this metric and we used our analysis and our subsequent discovery of how to calculate. Well, we spent a lot of time on learning how to calculate the connection coefficients, and we calculated the connection coefficients for every geodesic equation. There are 4 geodesic equations. As remember, these indices sum, the mu and the nu sum out. So all you're left is with a beta, and we're in 4-dimensional space-time. So we calculated all of the geodesic equations so by the end of lesson 22, we knew all 4 geodesic equations for the Schwarzschild spacetime. And in fact, here are those 4 equations that we derived directly from the geodesic equations. One is in the time variable, one is in the Schwarzschild radial variable, the polar variable, and the azimuthal variable. Then we proceeded to lesson 23. So in lesson 23, what we did is we took these geodesic equations, we took these 4 equations, made some assumptions that were motivated by the symmetry of the problem. In particular, we set theta equal to pi over 2 and theta dot equal to 0. And that we've seen in our classical work that we just did, we motivated that very precisely in the classical work, but it carries over logically right here. So that simplification really tore down a lot of the sophistication of these geodesic equations. And then when we solved for 2 of the geodesic equations, we discovered these constants of the motion. So the constants of the motion emerged from here after this term went away, and the constant of the motion emerged also from here. And remember, these geodesic equations came from the Euler-Lagrange equations, which came from a variational principle. The difference is that the Lagrangian that would stimulate all of this has no what did we call it in the classical analysis? It has no physical potential V, right? We didn't introduce a physical potential like in the classical case. We introduced a constant over R, I think with a minus sign in front, depending on the convention of how C worked. But we had this physical potential, and then we also ended up with an effective part, a fictitious potential, and we put them both together, and we got a effective potential. So we had a fictitious part and we had a physical part. So physical, and then we had a fictitious part. And I think the fictitious part went over r cubed, right? And so, the point being that we don't have a physical potential now. All we have is these geodesic equations, which were derived through an analysis of a path in space-time. But it is worth understanding that these are connected relationships. And I think we'll pause here to have a look at that. First, remind yourself, in the classical case, this is what the Lagrangian looked like for the central force problem, where the potential, I'm writing here as u of just the radial coordinate. And I'm talking now about the classical case, so I'm using r, which is just our standard radial coordinate, not the Schwarzschild coordinate. So what we have here is, this was the Lagrangian we developed all of that work in our past few lectures about classical mechanics from. So you can imagine, if we take away the physical potential, right, if the physical potential goes away, which let's just say it's the gravitational potential of a planet or something, you're still left with this piece of the Lagrangian, which is the kinetic energy. And the kinetic energy it's never going to go away. If you're in empty space and you're moving, you still have that piece of the Lagrangian, and therefore you can still solve using Lagrange's equations and the Euler-Lagrange equations for all the equations of motion. But let's look at the way this kinetic part of Lagrangian is constructed. We can take the constants, well, not the constants, we can take the terms that are in front of the kinetic pieces, meaning the first derivatives of the independent coordinate variables. We can take these coefficients and we can give them the name G11, G22, and G33. And I can, of course, compress it in almost the obvious way. I can compress it into this metric term where x alpha and x beta correspond. x1 is r, x2 is theta, and x3 is phi. Right? If I'm going to use this Einstein sum convention, I'm going to have to homogenize the symbol for the different coordinates to exploit it, but that's pretty trivial, right? And then I define the metric to be diagonal, and there's only 3 dimensions in regular Newtonian space, so I don't need the 4th dimension, and all of the other terms are 0. So I can write this Lagrangian, this full-size Lagrangian for the central force problem in classical mechanics in this form. And then, if I stipulate, there's no gravitating matter, I'm left with this, right? And now all I have is the sort of the free space, empty space Lagrangian, whose only term is the kinetic term, right? Now, this is exactly what we did when we built the geodesic equations up from a variational principle in our general relativity analysis. We started from this metric. And this metric here is, in fact, the metric of flat Euclidean space. So if I'm working here in Newtonian calculation, I have flat Euclidean space, and this is the metric of flat Euclidean space in spherical coordinates. So I take the metric that I'm using within general relativity and I put it in there, and I've got the Schwarzschild metric, and I no longer have flat Euclidean space, I have a Schwarzschild geometry. But notice I don't have this term. At no point in general relativity do we put in the physical potential of the gravitating body. That's gone. The reason is all of the action of gravity is caught up in here. It's in here. And we're going to sort of see that unfold a little bit. But what is important and might be worthwhile to do if you're interested is take this expression, just the expression without, well, you can leave the potential in or not, it doesn't really matter, but take this expression and run the Euler-Lagrange equation through using this metric in the Euclidean Newtonian system. And you will end up with something that looks just like the geodesic equations. So the geodesic equations are not just particular for general relativity. You can use them in the Newtonian case. You just got to have the right metric. Just pick the right metric and you can do it. And of course, that should be obvious because the general relativity case should limit to the Schwarzschild geometry case should limit to the general relativity case in the circumstance where this metric limits to the Minkowski metric, and that would be in the cases where rho, the Schwarzschild radius, is really, really large. All of this stuff kind of reduces to the Minkowski metric, which isn't, by the way, exactly the same as, of course, as that's not the same as the Newtonian case. It's the Minkowski case, so you still have all that special relativity involved. But the limits, so it should limit to the special relativistic case. But anyway, so after we did the analysis in lesson 23, we found constants of the motion. And these constants of the motion are totally analogous to the constants of the motion we found in the classical circumstance. In fact, this one even looks the same, right? And this one's different. The energy concept is different, but nevertheless, we have two constants of the motion. That helped us take these four geodesic equations in total, simplifying a lot of the terms, and then creating the radius anomaly equation. So we were left with the radius anomaly equation, which is not the world line equation. It's the equation of the Schwarzschild coordinate with respect to the true anomaly. And it will give us a picture of what the orbits look like. So that's fun, and that's what we're going to work with for right now. Now, about this equation, I just want to show that it comes in many different forms and appearance. It can be put into many different forms. And I've done that here. I've shown all the different forms for the radius anomaly equation. The first form here is the one that we actually, I just showed in the other page, right? That's the one we derived straight up. Then we, I think in the next lesson, we converted that radius anomaly equation into the dimensionless form. That was a very easy fix. We just took the one dimension of our problem, which is alpha, right? And alpha was equal to 2m in dimensions dimensions where g equals c equals 1. Well, in dimensions where g equals 1, right? Because I still keep carrying the c around here, right? And then so we reconverted this into that form. So now we have a completely dimensionless left-hand side and completely dimensionless right-hand side. So to be consistent, I'll show that here. In lesson 24, we took rho and converted it to the dimensionless form, and that was rho equals rho over the Schwarzschild radius. And then we created chi, which equaled 1 over the dimensionless form of the Schwarzschild. I keep saying the dimensionless form over the the reciprocal of the dimensionless form of the Schwarzschild coordinate was what chi was. And we actually saw this analysis in our classical work on the central force problem, right? We saw this was definitely used to create the differential equation that led to those orbits. So if you followed through those lectures, this is not an unusual transformation whatsoever even in classical physics. So after we did that, then we ended up with this version of the equation. We ended up with the what I called the, I call it the star radius anomaly equation, where star is supposed to mimic this star here, and it's dimensionless. So this is sort of where we ended up. Well, no, it's not quite where we totally ended up. But we quickly we took the dimensions away. We created that equation. And then I showed, well, there's another thing you can do. If you look at this, you see there's a fourth power, third power, second power, first power. You can factor out a power, like right there, and then you can factor the entire polynomial into some roots, and you'll have some leftover constant up front. So you can write this equation in this factored form, and I stress that the roots will always, of course, depend on these coefficients, this +1, -1, the c squared alpha squared over h squared, c squared alpha squared over h squared times kappa squared -1, right? Those coefficients will determine what these roots are. So these roots can be determined. Now this ends up being a cubic equation. After you factor out this rho star, you end up with a cubic equation, which can always be analyzed through the so-called cubic equation of non-elementary algebra, because most of us did not learn about the cubic equation. We learned about the quadratic equation, but not about the cubic equation. But these can be factored, and in fact, what's interesting is you only have to figure out 2 of the 3, because for a cubic equation, one of the roots depends on the other roots. So you can find 2 roots, you can find the third. But of course, you could take this and just take its reciprocal and square root, and you end up with that form. So that's a trivial transformation, but it is something that we do a lot. I want to put them all down because the analysis of this problem does go through almost all of these steps. And they look dramatic, but what could be less trivial than taking the square root of both sides and then the reciprocal of both sides, right? So that's what that step is. Then we made this very important substitution, chi is 1 over rho star. When we made that substitution, we end up with what I was calling the chi equation. And that substitution is very important. And then we just start accumulating these constants into smaller expressions. Now, of course, when g equals 1 or c equals 1, then s is just m over h, right? But just for clarity's sake, and also because the papers I cite use these units, I left the units in there. But remember, as long as we're consistent, we can always say, okay, we're going in the case where g equals c equals 1. So that's the chi equation. Now, just something I didn't talk about in that lecture, but I definitely do in the book Why Does It Move, and also here I might as well show it now. That's what this is from, by the way. This is from the book Why Does It Move. Chandrasekhar's text does this same analysis and comes basically to the same place, but you'll see Chandrasekhar is not quite as worried about getting it into some mathematically pure state. He likes to keep physical intuition floating around, or not. Maybe, you don't have to do this. And his expression, of course, chi is u in his textbook. This 2m, which we would call alpha, stays out front, and but you can see it's generally quite similar. So if you gathered up these constants correctly, you would end up with the same expression. But he likes to carry 2m around instead of alpha, and he doesn't squeeze everything into this variable s. But what he does do that's really special is that when he factors this, right? Because this could be factored too, right? This is a cubic polynomial, right? Cube term, square term, linear term, constant term. You could factor that. And when he does factor that, he does it in this really interesting way where he keeps an epsilon and an L, an epsilon and an L. So this is the root. 1 minus epsilon over L is the root. 1 plus epsilon over L is the root. And then 2 over L minus 1 over 2m is the third root. And what you'll notice, by the way, is that this third root, there's only 2 unknowns here, epsilon and L, epsilon and L, and L. And that's because, as I said, the third root depends on the 2 other roots in a cubic polynomial. It's a little known but important fact that shows up here. And this L is the semilattice rectum, and epsilon is the eccentricity in the classical model. And so he's setting himself up to understand how the eccentricity and the semilattice rectum are different in general relativity. So he likes to keep it this way. We don't study it that way, but just be aware that you can see much more tricky breakdown. So what we just call rho, what we're just calling as the root, he breaks down into these pieces that are dependent on orbital parameters. And of course he does this in the front end because he knows how it's going to end up, right? So but if you look now, let's see, what do we have? We also have caustic, which is one of the very important papers that I learned all this from. Caustic takes this guy here. Well, this is caustic, really. But from this equation right here, if you take the square root, you you can take the square root of this, right? That's easy enough. And then you can kind of factor things out to be in this form. And if you look carefully, you'll see you'll see x cubed, chi cubed in front, minus chi squared, and then you'll see a plus or a minus beta chi, right? And that would be this guy, and then alpha squared, which would be this constant. So you can see how beta and alpha would be related to 4s squared and 4s squared. And then you could, what do we do next? Oh yeah, you could take this guy, and instead of writing it like that, the reason he wrote it like this is he has a motive, right? There's a motive for writing it in this form in his paper. But I'm just trying to demonstrate that this equation shows up in lots of different forms for different purposes. So he has a motive for this. And then, but he says, but you can always write this as a factored form with 3 separate roots, which is basically akin to the reciprocal of this, right? So you can do that too. These are really kind of trivial changes. Now, what's not a trivial change is what we kind of showed in one of the later lectures, which is this p equation. This p equation requires a substitution that is known from advanced algebra, and the p equation, we discussed that in depth, I think, in lecture 24. I'm sorry, I meant lesson 25. So in lesson 25, we took the result of lesson 24, which was this equation here, and we worked to turn that into this equation here. And we used this substitution. That substitution applied to this equation gave us this equation. And that brought us to the sort of an actual answer that allowed us to calculate the key quantity of interest, which was rho of phi, the radius anomaly expression. And that turned out to be this object. It turned out to be the Weierstrass P function, plus a 12th in this to the power minus 1 times alpha over 4. And that was our first attack at solving the differential equation. This differential equation ultimately led back to this. And it took a few reverses, right? We had to reverse this substitution here, right? We had to reverse the substitution for u to replace it with chi. Then we had to reverse the substitution for chi right here. We had to reverse this guy. First we had to reverse this, then we had to reverse this, and ultimately we ended up with, and then we had to actually reverse phi star back, or rho star back to rho, right? And when we do all those reversals, we ended up with this expression right here, which was our first real solution of anything. And this will give us a function of the radial distance, well, I shouldn't say distance, the radial coordinate given the true anomaly. So it's a radial coordinate as a function of the true anomaly. It's not exactly the world line, as I said a couple times before, but it's definitely progress. And then we also discovered the formula for the coordinate time as a function of this inverse dimensionless Schwarzschild radial coordinate. And that was this thing, right? And here we see in the denominator of this, we put we had worked in that lesson 25, to demonstrate the use of this form here of the caustics equation, right? We used that form there, so we had A and B well defined. And then we discovered this differential equation for dt d chi, and then we realized that the same differential equation almost for d tau, the proper time with respect to chi, would be this, but you add 1 over a factor of the energy right there. So with all that in mind, that's where we stopped and then said, you know what, let's go back and look at the classical problem. Clearly the wrong order of things, but if I did things in the normal order, then this would be a normal class and you wouldn't be interested in any of this, right? A little bit out of order is fine because it causes your brain to remind yourself, rethink, reconnect. It's okay to do things a little out of order. It stimulates forgetting and remembering, which is really the only way to ultimately remember, ironically. Okay, so that's where we kind of ended up with the general relativity stuff. One possible path forward is to start studying. Okay, we can study. Let's attack and see if we can understand that Weierstrassian p function or some other version of the radius anomaly equation. So we have that, the radius anomaly equation for chi as a function of the true anomaly. We could also attack since we have these guys now, would I write them now? Since we have these guys here, we could attack them and solve for tau as a function of chi. So I could be looking for the proper time as a function of this radial variable. I'll call this thing the radial variable, but remember it's 1 over rho star, right? Or we could do the same thing with the proper time. We could find the proper time as a function of the radial variable. And presumably then, if we did all of this, then I could reconstruct the world line, right? I could reconstruct the world line. I would put the coordinate time along this axis. So whatever coordinate time I calculated for a radius, I would put the radius along this axis, and then I would get something. And then I would put phi, of course, along this axis. So I would end up with sort of a projection of the orbit on this plane. Whoops. A projection of the orbit on this plane, like this. Just pretending it's closed. I know it's not. And then when I put the time in there, then the orbit will sort of wrap around the planet in some sort of spiral form if it was a closed orbit. And then for the proper time, I can then mark at each different point. I could say proper time equals coordinate time, which we set to 0. And then I could just mark even units of proper time along this path based on this equation as well. So I could capture the world line with this, and that's really what I kind of want to do. So I could do that. That's the next, that's one possible way forward here. And but there's still some more general analysis to do before we attack these equations. These things are hard. It's going to be a lot of analysis, a lot of really esoteric math. We can actually go backwards a step and we can start working on something that looks a lot more like the classical problem, which is only available to us because of the spherical symmetry of this case. So that's what we're going to do. We're actually going to attack a different angle first, and then we'll come back to this problem because this is really hard. All right, to begin this part of the analysis, we are going to go way back to the raw orbit equation. That's what I call it, the raw orbit equation. This is what we derived once we went to the geodesic equations and we made all the replacements for the constants of the motion, right? Here's one constant of the motion, this kappa, and then this alpha. This was associated with the angular momentum, and this is associated with the energy. Specifically, this guy here is the energy per unit rest energy of the particle that's falling in our field, and h is our angular momentum. So the raw orbit equation, we use that, and from that raw orbit equation, we ultimately derived every one of these guys, right? All of these guys ultimately came from the raw orbit equation, and these are all the different versions of the radius anomaly equation. But the geodesic equation led to the raw orbit equation, which led to everything else. So we're kind of going back to that in order to take this next step forward in a slightly different direction. So we can shuffle this around a little bit. So we can write it in this form, which is not very different. We're just sort of expanding the things out a little bit and moving some constants over to the right-hand side. But once we're in this form, we can think about multiplying by, well, the mass of the test particle over 2. Remember, it's the test particle that's moving with rho dot, right? And if I did that, I would put an m over 2 here, an m over 2 here, an m over 2 here, and an m over 2 here. And that helps me sort of interpret things a little bit. This looks like a kinetic energy, and this looks like a this actually looks like, well, here we have an mc squared, right? So there's a rest energy there, and here's a rest energy here. That's one of the nice reasons of keeping the c squared, is because you can see the rest energy, although the fact is m itself is the rest energy in units where c equals 1, so it's really not much of a big deal. But once you have this, we start thinking of this as a kinetic energy term. We think of this as some sort of potential energy term, potential energy, and then we think of this as a constant that needs a little bit of interpretation. So but that's how the m over 2 will help us. But if we get rid of those m over 2's, we put them in there to help us do the interpretation, right? The kinetic energy, potential energy, and this constant. But this idea of putting the m over 2 here, signaling that this is a kinetic energy, we start thinking of this in terms of kinetic potential energies summed together being a constant, which is a very familiar thing from classical mechanics. So with that interpretation in mind, let's move forward with just the black pieces of the equation and simplify it to a new form. And this is the new form. Now we are enforcing c equals 1, so I got rid of the c's. And now we can think about this side here as being the total energy per unit rest energy. The units are squared, right? So that gives us sort of a squared total energy per rest energy. This is still the kinetic term, and this is still the potential term. So we think about this guy as the value of kappa squared, where the kinetic piece is equal to 0, right? Because if I took this and put it on this side of the equation, right, if I move this over here, I'd get a minus sign. And so this would represent the value of kappa, where we would end up with rho dot squared equals 0. So there's no kinetic energy. So that when rho dot squared equals 0, there's no radial motion, and that's a turning point, right? So we can think of that as that value, this as that value of kappa squared, which accomplishes a turning, or which identifies a turning point. And the reason we can call it that is because this, of course, is a function of rho. So at some value rho, well, you pick a value of rho, you move it over here, and then that value of kappa that equals this other term that would be a turning point, right? So for every value of rho, there's a corresponding energy that makes that value of rho a turning point. Is that the right way to say it? Well, we're going to graph it in a moment, so it'll be pretty evident. The point is that's how we think of a potential in the classical problem as well. We think of the turning points being that spot where all of the energy is potential energy and there's 0 kinetic energy. There's actually 2 ways to define the turning point in this problem. You could call this guy here v squared, and we're looking for when v squared equals kappa squared, and you solve that. This is of rho, right? And you solve that for rho. Likewise, we could set it up just so v of rho equals kappa, and that's what we're going to do. We're going to do v of rho equals kappa. So we're going to call the effective potential essentially the square root of this thing, right? Because ultimately we have rho dot squared equals kappa squared minus 1 minus alpha over rho h over rho squared plus 1, right? So when this side equals 0 is what matters. So we're going to actually look at when kappa equals the square root of this stuff here, right? That's what we're going to do. So in effect, that means we are going to study the expression rho dot squared plus v squared of rho equals kappa squared. And v, well, remember, I put that square root in there as for demonstrative purposes. So v is going to equal this thing right here. The square root of that. That's what v squared is going to equal that thing right there. So v of rho is going to equal, let's use the feature here. It's going to equal this thing right there. So there we have it. V of rho equals the square root of that guy. Now, in order to crunch this a little further, to make it cleaner for graphing purposes, I'm going to introduce a couple of simplifications. I'm going to introduce the reduced angular momentum, which is going to be h over alpha. Remember, h is measured in units of distance, and so alpha is the only different distance in our problem. So the reduced angular momentum, and that will be h hat. So h hat is the reduced angular momentum. I'm going to set c equal to 1 everywhere, finally. And then we're going to reintroduce, of course, chi is alpha over rho, or 1 over rho star. So we're going to reintroduce all of those variables, and then we're going to get v of rho equals this expression right here. So this guy here is entirely equivalent to this with the reduced angular momentum, which is nice because now the angular momentum itself is also dimensionless, which is very convenient. And c is 1, and we have the standard chi. We'll call this the radial coordinate, but it's really, remember, the reciprocal of the Schwarzschild radius measured in units of, it's the reciprocal of the Schwarzschild radial coordinate measured in units of the Schwarzschild radius, which is equal to 2m, right? Alpha was equal to 2m. So this is the potential, right? And we can now plot the potential energy as a function of r. All right, so in the next lesson, we're going to study this collection of potential curves. As a warm-up, just to see, this is our basic expression. The kinetic energy per unit mass, this was the potential energy squared per unit mass, right? And then this is the total energy per unit rest mass energy squared. So we're interpreting the potential. We've decided to write the potential in this form. We could do without the square root, right? The square root just kind of shrinks everything a little bit, but we're going to interpret it in this fashion. And this k squared is this energy per unit rest mass, which we call E on this axis. So I should, this could be understood as kappa. And then down here, I have rho over m. This equation here is the same as this equation here, where I've already just sort of made the replacement alpha 1 over rho, alpha over rho. Let me get rid of all that crap. It's alpha over rho, right? So I've made that substitution back into here, but I've kept the reduced angular momentum. And the reason is because I want something that looks like you can kind of interpret as a radius here. Notice that this is logarithmic, right? Because to get the shape of the curve and the distance is difficult. So we have a logarithmic rho. And this is rho over m, which is not the same as rho over 2m, right? It's only rho over m, the mass of the central star. So it's not the Schwarzschild. So the Schwarzschild radius happens at 2m. So the Schwarzschild radius is actually at 2 instead of at 1. And I do this because that's how it was done in Wheeler's book. So I wanted to make sure my graphs were accurate compared to his. So I graphed it the same way. And so this expression here is these curves for different values of h. Remember, for different values of angular momentum, you see different potentials. And for h equals 0, you see this attractive potential that's exactly the same as you would see in classical mechanics and would basically just represent what we call a plunging orbit directly just sort of going right into the center, just straight up falling. But as soon as you add a little bit of angular momentum, this curve starts to bend up, and we'll talk a lot about this next time. But what you see is it has a lot of the features of the classical case. The big, huge difference is this bump right here, So you can have so much energy that as you get closer and closer to the object, you go right over the angular momentum barrier and you get sucked into the central potential. This pit in the potential doesn't exist in classical mechanics. But the other thing to notice, of course, is that everything is the effective potential. There's no so-called physical potential. This whole thing is due to the nature of the metric and the nature of space-time. And so there's no longer any actual physical potential combined with potential due to just the coordinate system you're dealing with. This is all dealing with the coordinate system. Well, you shouldn't put it that way, because it's really the structure of the space-time itself. Normally, in flat space-time, you're dealing with the same issue. You still have you could have many different coordinate systems even in flat space-time. So it's not purely the coordinate system, but it's the fact that space-time itself carries all the information about the gravitational potential. Now, if there was an electromagnetic potential involved, then that would be an additional physical term. But if it's a gravitational term, we've wrapped all of that up in the metric. And that's all contained in the geodesic equations, which in flat spacetime would just be straight lines. Okay, so we're going to talk a little bit about this and what this can tell us about the different orbits in our next lecture.